Our third speaker is Guohao Dai. I hope I'm not pronouncing it wrong. Sparse computing drives energy efficient computation for artificial intelligence.
，take badge off. Okay. Okay, so very glad to be here and to be the last speaker today to present our work on sparse computing. I'm Guohao Dai from Shanghai Jiao University, and currently I'm also the co-founder of a startup for AI infrastructure in China. So today I'm very glad to share some representative works in our group in the past few years on sparse computing. So let me first introduce myself. I graduated from Tsinghua University at 2019, and when I was PhD student, I'm working on the graph processing. So there's a kind of data structure which is sparse. And when I was a postdoc, I'm considering about how to apply the sparse computing into some neural network architecture research and also some AI applications. So I'm working on some graph neural network acceleration. And now I'm an associate professor in Shanghai University and working on both sparse architecture design, something like the hardware design, and also the sparse system designs for the artificial intelligence. So let me first go through the background of my research. As we can see that because we are providing the computing resource for the upper algorithms like artificial intelligence algorithms, so I need to look into the trend of artificial intelligence. So as we can see here, in the past 5 years, AI computing demand has increased by 4 to 5 orders of magnitude, but as a computing supply for the AI applications, the chip performance growth has slowed down a lot. So there is a huge gap between the demand and the supply, between the algorithm and the chip. That's the challenge we need to face. And currently we are moved from the AI 1.0 era to the AI 2.0 era. So what are two eras? What's the difference? For the AI 1.0 era, there are a lot of different algorithms for different kinds of applications. For example, we have convolutional neural networks for the for the vision tasks, and we also have other neural networks for different kinds of tasks. So the algorithm is different for different applications. But now we are moving to the large language model era, that's AI 2.0. The difference is here that we can use one large model that is called the foundation model for different kinds of applications. We can use transformer to process vision, to process audio, video. We will show a lot of examples in the future slides. So the difference lies in the algorithm. We use different algorithms for different applications in the first era, and now we can use one algorithm for different kinds of applications. That's the difference. And to fully understand the difference, we do a lot of survey on the system and also the accelerator performance for these two areas. As you can see on the left, that is for the AI 1.0 era, and on the right is for the AI 2.0 era. And we also did a lot of survey on different kinds of performance for the system and chips. You can see for the x-axis, that represents the power for a system of a chip. But for the y-axis, that's the difference. For the first area, the y-axis is the throughput. That means how many operations can be processed on the chip or the system. But for the AI 2.0 era, the y-axis becomes how many tokens can be processed under the same constraints. So that's the difference. So the optimization targets for those two different areas is different. So we will show the difference in our slides. So let's first look into the sparse computing in the first era. In the AI 1.0 era, typical networks like convolutional neural networks and transformers can be abstracted using a lot of different matrix multiplications and can be mapped onto hardware for execution. So if we can leveraging the sparse computing in the matrix multiplication, we can reduce the total computing and also the memory access demand for the operations. For example, you can see here on the roofline model, we can improve the equivalent computing power and computing capacity for the hardware using the sparse computing. So we can see a lot of work has working on using the sparse computing for the system and also the hardware. And typically we can use sparsity for activation and also for ways to reduce the data transfer and also the computation requirements. So let me first introduce our work on the sparse operators for the first era. This is work we have done when I was a postdoc in Tsinghua University working on the sparse matrix multiplications on GPU for different kinds of inputs, that is input dynamics. So in the AI 1.0 era, models such as convolutional networks and MLP and others will use weight sparsity that is using the pruning operations to reduce the total operations for the matrix multiplications. And some applications, for example, the point cloud and the graph neural networks will use the sparse matrix multiplication to process the inputs. So the sparse matrix multiplication is the key operator in the computation, especially for the first era in the AI. But the challenge is very huge. As we have also mentioned in previous slides and previous talk, the different kinds of input, especially the different inputs, different formats, and also different kinds of data access pattern will lead to different performance on the same configuration. That's why we need the compilation tools. So here we show a typical example. Here we use different APIs and different configurations from the NVIDIA cuSparse library to process the matrix multiplications under different configurations. And also here we measure the performance of different APIs and different configurations for different data sets and normalize the performance to the performance with to the APIs with the best performance for each data. So if we have one API or one solutions for different kinds of inputs, the result should be 100%. That means we will achieve the best performance for different inputs, but the results is not that good. We find that not one API can achieve the best performance for different inputs. And even on different configurations, the best API is different. So that means we cannot use one API or one solution for different inputs to get the best performance. So that's a problem. So how to solve these problems? We formulate the algorithm space for the sparse matrix multiplications. For example, I only take the sparse matrix multiplication as a very simple example, and we can see that the sparse matrix multiplications can be formulated using 3 loops. The outer loop for the to traverse each row of the sparse matrix, and the inner loop to traverse all elements. So that's here. So let me take the outer loop as an example. Because we have a lot of threads on GPUs, so how to assign the workload to different GPUs, that's a problem. So we have 2 typical implementations for here. The first one is we assign each row to 1 thread. So that's the first implementation. And the second one is we assign same elements to different threads. That's 2 typical implementations. And these 2 implementations will lead to different performance. For example, if each row is balanced, we will not suffer from the unbalanced problem. We will not suffer from the unbalanced problem here, right? But if each row is unbalanced, we will suffer from the synchronization overhead from the first. Okay, looks good. Okay, so I mean here, different implementations will lead to different performance on the different input dynamics. So for each loop, we find that we have different kinds of inputs, and each input will lead to different performance. So we will formulate the, we will get different implementation for the sparse matrix multiplication on GPUs. So how can we choose the implementation with the best performance? How can we do that? So here we train a very simple model to dynamically and heuristically choose the API, because we can get the performance prediction with some statistic inputs here. So here we train a model, and this model will dynamically choose the API, the solution with the best performance here. And follow this idea, we implement a lot of GPU kernels for the sparse processing on GPUs using different kinds of optimization, like the coarse grain optimization, input dynamics, and also some efficient reduction algorithms. And if you are interested in it, you can scan the QR code for the whole project. And here is the performance. We integrate our design into some graph neural network frameworks and also some sparse matrix multiplication libraries. Here we compare our performance with some commercial software solutions. Here should be DGL for graph neural network processing, and we compare some solutions with NVIDIA commercial kernels. We can achieve the performance speed up compared with them. And now we move on to the second era for AI, the foundation model era. Before I introduce our design, let me first introduce what is a large language model, what is the foundation model. The foundation model uses a transformer architecture to autographically generate the output that is a token. So the typical operation here are consisted of two parts. The first one is attention or multi-head attention, and the second one is FFN, that is a dense matrix multiplication. And we also find that there are different kinds of the foundation model. The first one is large language model, and the second one is we use the large transformer for the video or the image generation. So the roofline model for these 2 kinds of models are different. For the first one, it is the first large language model, it is memory bounded, and the second one is computation bounded. So how to optimize these 2 kinds, that's different. So the very simple idea for us is if we can apply the sparse matrix multiplication or the sparse pruning for the large language model, we can reduce the total computation overhead. But the problem is very huge here. The problem is we cannot spell the performance degradation for the accuracy. So there is a very different consideration between the researcher in the algorithm domain and the researcher in the circuits or architecture domain. For the researcher in the algorithm domain, they say, hey, we do not want any constraints for the sparsification or the pruning, right? So they want the unstructured sparsity. But for the people like me working on the circuits architecture domain, we say, hey, we do need structure sparsity because the overhead for the system or the circuits is very, very low. So how can we combine these two perspectives? We point out that we can combine these two perspectives together because for the algorithm guy, they only look into the coarse grained sparsity. That means the whole matrix should be unstructured rather than a tiled matrix should be structured. But for the circuits guy, they say we only need very small matrix for structure. So can we use different small structured sparse matrix to formulate a very huge the whole unstructured matrix? That's our idea. So follow this idea, we publish a paper working on the large language model acceleration for inference on FPGA for the demonstration. So follow this idea, we ensure the structure sparsity of the flexible structure sparsity for the attention and also the linear parts. And also we apply this design onto the DSP chain on FPGAs. That's something about the hardware. And we also use some fusion kernels or fusion operations to reduce the upstream memory access based on our sparsity pattern. And here you can see, using this idea, we can accelerate the large language model inference with the sparsity. Here we compare our FPGA design. It is a very, I mean the price and the process for this is very low. You can see it is 16 nanometers compared with GPUs. But the energy efficiency, the quality efficiency, and the throughput is better than GPU. That's the sparsity brings us. And now we come to the video generation. It is another very popular algorithms in the past and this year. For video generation, the difference is the problem becomes computation boundaries rather than the memory access boundaries. So how can we reduce the total computation? So I remember when I was an undergraduate student, research on video is already very popular at that time. So many well-known techniques have been proposed in that domain and compress the total size of videos at least 1,000 times. So that means we do not need to propose very new ideas. We can stand on the shoulders of the giants. So how can we do this? The idea is very simple. The insight is here because we can reduce the total computation overhead by explore the similarity between the videos. That has already proved to be true in the video compression domain. Okay, so we propose our hardware design for the video generation based on this very simple insight. And this paper was published in this year FPGA 25 conference and win the best paper awards. So we apply this idea here. We explore the similarity in the inter the frame and also intra the frame. So that's a similarity here. We use some flag or some flag frame here to represent the similarity, and we do calculate the similarity on the fly. And we also combine our sparsification design with the quantization design together to fully utilize the hardware resources. And as mentioned previously, we also know that the sparsification will leave some workload on balance So we also propose our adaptive scheduling to handle these problems. So that's a huge problem will be bring by the sparsity, and the online scheduling will solve these problems. We can see here is a result. We compared our design with some state-of-the-art design, and you can see from the metric we do not lead to very huge, we only lead tiny accuracy loss, but we can see here compared with the original video generation, our design will lead to similar results, because for the video generation, we do not need that exactly the same accuracy, but the similar video generation quality, that's enough. So you can see here, compared with GPUs, the peak performance or the throughput for the hardware is nearly 20 times lower from our hardware perspective, but by applying our sparsification, quantization, and scheduling after sparsification, apply 3 techniques, we will improve the performance by about 27 times. That means the end-to-end performance will be 13% higher, even with very low computation capability FPGAs. So we can improve the video generation speeds if we can turn all the design into ASIC and integrate them into the system. So here comes to the summary. Today I introduced 3 typical papers of ours for the graph neural network acceleration, large language model, and model with multimodality. And the key insight behind all these designs is similar. We want to improve the equivalent computation capability for the algorithm. That means the algorithm skyrockets every year, but the chip is not that fast. So how can we fully utilize the hardware to support the algorithms? We use some GPUs or FPGAs with lower computation capabilities, but the end-to-end performance is much more better. And I also want to say that the sparsity is not only leading to a better efficiency, but leading to a better intelligence. You can see here is AlphaFold and also the DeepSeek, which is very popular this year. They all use sparsity to get a better model rather than get a model with a better efficiency. So that means the sparsity is natural in the real world problems. So how can we fully utilize this? How can we fully understand this? That's very important for the future AI. So that's all about this talk. And my group is working on the sparse computation for a long year. So if you want to get some contact, we can discuss through this website. Thank you.